4. Last period we have studied the Mayer's relation. In Mayer's relation, we have proved that Cp minus Cv is equal to R. This is the Mayer's relation. That means difference of the two specific heats, that is specific heat at constant pressure minus specific heat at constant volume, is equal to R. In both, that is principal and molar specific heat, we have proved. Today we are going to see about relation between these two, but we are going to obtain the adiabatic constant gamma, which is equal to Cp upon Cv. Now here we prove this, or we obtain values of gamma for 3 cases. In that we consider first case, monoatomic gas. That means here we consider only one atom of the gas, and you know that is for monoatomic gas there are 3 degrees of freedom. 3 degrees of freedom. That means total energy, total kinetic energy is divided in 3 ways. Therefore, average energy per atom is, we can write here, 3 by 2 kb into T, or we can write here E is equal to 3 by 2 Na kb into T, where Na is number of atoms. Now here molar specific heat at constant volume Cv can be written like this. Cv is equal to T by dt, which is equal to 3 by 2 Na into kb, or we can write here 3 by 2 R. Now you know that is Cp minus Cv is equal to R, and therefore from this equation if we put the value of Cv here, then we get here Cp is equal to 5 by 2 R, and we obtain the ratio gamma. We call it the adiabatic constant. Gamma is equal to Cp upon Cv is equal to 5 by 2 R divided by 3 by 2 R. Here this 2 gets cancelled. Here we consider, suppose this 2 gets cancelled, R gets cancelled, and we get here Cp upon Cv is equal to 5 by 3. This is the adiabatic constant for monoatomic gas. Now we consider next case, that is diatomic gas. And in this diatomic gas, that means it consists of the 2 atoms of the gas, we consider that is 2 cases, rigid and non-rigid. Rigid diatomic gas and non-rigid diatomic gas. See here, for rigid diatomic gas there are 5 degrees of freedom. 5 degrees of freedom. Therefore, average energy per atom is 5 by 2 kb into T. This is the average energy per atom. And the total internal energy per mole can be written like this. E equal to 5 by 2 Na kb into T, where Na is number of atoms. Now C, phi, which is equal to d by dt, which is equal to, we can write here 5 by 2 R. And again, if you know that is Cp minus Cv is equal to R, therefore Cp is equal to, we get here 7 by 2 R. And adiabatic constant gamma is equal to Cp upon Cv, which is equal to 7 by 2 r divided by 5 by 2 r. Again here this 2 cancels with this 2, r cancels with this r, and we get here gamma is equal to 7 by 5. This is for rigid diatomic molecule. Now we consider here for non-rigid. Here for non-rigid diatomic molecule. Here you see for non-rigid diatomic molecule there are 7 degrees of freedom. There are 7 degrees of freedom. And the energy per molecule can be written like this: 7 by 2, we can write here 7 by 2 kb into T. That means E is equal to, we can write here 7 by 2 Na kb into T, and therefore we get here Cv is equal to 7 by 2, we can get here R, and therefore Cp can be written like this 9 by 2 R, and therefore adiabatic constant gamma is equal to Cp upon Cv, which is equal to 9 by 2 R divided by 7 by 2 R. Again 2 gets cancelled, R also gets cancelled, and we get here gamma is equal to 9 by 7. This is the for diatomic gas. Now we consider third one, polyatomic gas. Polyatomic gas. Here you see for polyatomic gas we consider here number of atoms are there, then there are 3 degrees of freedom, and we consider again the F 3 plus F degrees of freedom. That means we get right here 3 plus F degrees of freedom, and total energy E can be written like this. That is, we can write here E is equal to 3 plus F Na kb into T, and Cv is equal to, we can write here dE by dt, which is equal to 3 plus F into R, and therefore Cp is equal to, we get here 4 plus F into R, and if you obtain the adiabatic constant gamma is equal to Cp upon Cv, which is equal to 4 plus F upon 3 plus F. R gets cancelled. This is all about the energy or gamma, adiabatic constant gamma for monoatomic gas, diatomic gas, and for polyatomic gas. Now we consider next thing. We consider here next article, radiation. Here you see there are 3 ways of transfer of heat. First way, conduction. Second way we consider convection, and third way we consider radiation. That means heat flows from one place to another place by these 3 ways. First is conduction, second one is convection, and third one we consider it is radiation. Now we will see one by one. Here, in case of this conduction, suppose we consider a metal rod this is the metal rod. Then suppose we heat this rod at one end. Then after some time this end also gets heated. That means in case of conductor there is transfer of energy from one particle to another particle without actual displacement of the particles, and this is possible in all metals. That means metals are good conductors of heat and electricity, and this way, that means transfer of heat energy from one place to another place, not actual displacement of the particle. In case of these metals or conductors, this way we call it as a conduction. Now we consider convection. Suppose you consider there is a water or in this container. Suppose this is the water in the container, and suppose we give heat to bottom of this container. Then what happens? The molecules or atoms near the base of this conductor gets heated. They becomes lighter and moves in the upward direction. And at the same time, these molecules having low temperature, they move into the downward direction. Again, they get heated. In this way, the convection current flows. This type of convection is also possible in case of air, and whites can flow from one place to another place, and that current we call it as a convection current. Convection current. Here, in case of convection, the heat flows from one place to another place by actual displacement of the particle, either liquid particles or air particles. Heat flows, and this way we call it as a conduction. Here, medium is necessary, but they are conductors. No actual displacement of the particle in case of conduction, but in case of the convection, the medium is necessary, and also there is actual displacement of the particle. Now we consider the third way of transfer of heat. We call it as a radiation. Here, heat energy is radiated from one place to another place in the form of electromagnetic waves. And this way we call it as a radiation. Now here, heat waves have wavelength that is higher than light waves. Heat waves have wavelength higher than light waves and smaller than radio waves. That means we consider here, suppose this is the heat waves. Then they have wavelength higher than light waves and smaller than radio waves. This is the wavelength of the heat waves. Now the wavelength range is near about 7.3 into 10 raised to minus 7 meter to, we can write here, 2.5 into 10 raised to minus 3 meter. Heat waves have wavelength in between these. And the mode of transfer of heat from one place to another place in the form of these electromagnetic waves, we call it as a radiation. And we discuss this radiation here in this subtopic of the kinetic theory of gases and radiation. This is all about the radiation. This is the introductory part in case of radiation. In next lecture, we are going to discuss clearly about what is meant by absorption, reflection, transmission, its coefficients. Okay, thank you.